In this video, we're going to discuss resting membrane potential. When you're done, you should be able to describe the concentration of sodium and potassium, describe the role of Nernst-Goldman in the resting membrane potential, list major voltages across the membrane. That includes the Nernst potassium, Nernst sodium, the resting membrane potential, and threshold. Describe hyperpolarization and hypopolarization. So let's begin with the membrane. And make a voltage chart down here. You learned from the previous video that the Nernst potassium is negative 90 millivolts. Nernst sodium is plus 60 millivolts. We look at the concentration of sodium. You have 145 milliosmoles outside the cell and 15 inside. For potassium, you have 150 inside and 5 outside. Those are your concentrations. If one opens up a gate for sodium, you cannot have a flow of sodium across the membrane into the cell. As we learned earlier, if there's a flow, there's a current. And the greater the flow, the greater the current. So let's begin at 0 voltage. This is voltage scale. There's no movement of any ions, therefore the voltage is 0. If we were to allow sodium to come in unimpeded, it goes towards its Nernst, which means the voltage of this membrane should go towards our average plus 60 millivolts. If it's just leaking in, as it is, if it's just leaking in, since there's going to be a flow, it's kind of restricted, but since there is still a flow, you still have a voltage towards the positive, towards that plus 60. If you look only at potassium, there'd be a flow out of the cell due to the concentration gradient. And again, there's a flow, there's a current, there's a voltage. If we were to have unimpeded flow, the voltage would reach negative 90 millivolts. But this is not unimpeded, it's just leaking, just like a little leak. So since it's a leak, it'll still go towards negative 90, although it won't reach negative 90. So the Nernst equation is how the movement of each of these affect each individual ion. So as sodium increases flow rate in, you'll go closer toward, make the membrane go closer toward 60. If sodium increases its flow out, you'll make the membrane potential go close to negative 90. The Goldman equation is that you combine both of them. So what you see happening is, as potassium is flowing out of the cell, it's going to attempt to make the voltage go toward negative 90. Well, as sodium comes in, it's going to drop this voltage back towards this direction. So there's a balance between potassium and Nernst going this way and sodium going this way. In fact, when it's said and done, it stops here at negative 70 millivolts. We call that the resting membrane potential. So nerve cell at rest, that doesn't mean nothing's happening. You still have the sodium leaking in, potassium leaking out. But when you combine both of these, the voltage is at negative 70 millivolts. Now when we look at, for a nerve impulse to occur, it has to reach a very critical stage here called threshold. The threshold voltage is negative 55 millivolts. So if the actual voltage of the cell gets to negative 55, then the actual potential will begin. We'll discuss that in the next video. Until then, we begin at negative 70. If we're to decrease the flow of potassium out, the membrane potential will go more in this direction. If instead you're to increase the flow of sodium in, it tends to go more towards sodium, starts to be more that way. So the voltage of the rest of the membrane can go back and forth. based on how the flow is on these two ions. Now let's say we increase the flow of sodium into the cell. That's going to make this membrane potential go this direction. So going, let's say you go to negative 60 millivolts. Since this is less negative, we say it's the cell being hypopolarized. Hypopolarized. No, hypo means less. So if we move the membrane potential from negative 70 to negative 60, or even that direction, and make it less negative, then membrane is becoming hypopolarized. If, on the other hand, we move the membrane potential this way, let's move it to negative 80 millivolts. How do we do that? Well, let's let more potassium come out. More potassium flows towards unimpeded flow, goes towards this nernst, which is negative 90, but it's just leaking. So we do move the membrane potential, let's say, to negative 80 millivolts. That now is more negative than this. So it would be more negative. And we use the word hyperpolarized. So hypopolarized refers to the voltage of the membrane being less negative. That means going towards zero. Hyperpolarized means the membrane potential is going away from zero, more negative. So it's to be hyperpolarized. Now obviously, since the negative 55, when the actual potential begins, if you hypopolarize the cell, it'll make it get close to this and be easier to have a nerve impulse. If you hyperpolarize it and get the voltage away from the threshold, it'll be more difficult to reach threshold because it has further to go, therefore be inhibiting the cell from firing off. So the concentration of sodium and potassium. Sodium, you have 145 milliosmoles outside, 15 inside. That's for sodium. For potassium, you have 150 milliosmoles inside and 5 milliosmoles outside. Nernst Goldman, as sodium flows in, tends to make the membrane potential go positive. As potassium goes out, makes it go towards negative, towards this membrane, its Nernst equilibrium. And they combine at negative 70. By the way, since it's negative 70, you should realize that the sodium leaks out faster than sodium does. That's why it's close towards potassium's Nernst. Major voltages again. Nernst for potassium is negative 90 millivolts. Nernst for sodium is plus 60 millivolts. Resting membrane potential for neurons, nerve cells is negative 70 millivolts. Threshold, when the actual potential begins, occurs negative 55 millivolts. Hyperpolarization is you change this, it's no longer negative 70, let's say move to negative 80, that's more negative. The word we use for more is hyper, therefore it becomes hyperpolarized. It moves the resting membrane potential smaller, make it less negative. As negative 60, it's less negative. We use the word hyper for less, therefore it becomes hyperpolarized.